So question number 21 on page 196 says we have a holding pen being built alongside a long building. So I've shown the long building in blue here. And the pen requires only 3 fence sides. So we have the red fencing along those sides. And we have enough fencing is for 90 meters. And then we're trying to maximize this area in here. So we can kind of predict, and we can just guess at what the maximum area is. I can just kind of guess maybe that this is going to be maybe 30 here and 30 here. And if I have 30 and 30, I'm going to maybe make this 30 here. And I can say, well, this ended up being a square area if I do that. And maybe that will give me the biggest area if I make it 30. Okay, so we can just kind of play around with this and make a table of values even to see what would be the biggest. So we really want to write a function to model the area. To do that, we first off have to make sure we know how to calculate area. It's going to be length times width. And I'm going to generalize this, and I'm just going to make this equal to x. And so this side's going to be x as well. And so we can then express this side as y, as unknown. And we can just say that the area is going to be equal to x times y. Now, since we have some information about the length of fencing, instead of y, if these two sides are going to be x here and x here, I can just say that the y side is going to be 90 minus 2x. And I can just get rid of the y like that and just say the whole length is 90 minus 2x. And then I can rewrite it as now a function with one variable. And this is now a function where if I choose an x, I can calculate the area. So it looks like this. A of x, I've written as a function. I'm going to expand this, negative 2x squared plus 90x. Okay, this function, if I graph it, I'm going to find some maximum point which gives us the most area. So this would be A, and this would be different values of x along here. So to find the maximum possible areas, there's lots of things we can do. We can graph this, but I'm going to, in this case, complete the square to find the vertex. And there's other ways we can do this, but I'm going to use completion of squares. So I'm going to end up with x squared minus 45x when I factor that out, plus half of 45 squared is going to be 22.5 squared. And that gives me 506.25. Now I have to balance that off because I've completed the square, but I haven't balanced this equation. So I've added negative 2 groups of that. So I'm going to add, so I'm going to times that by 2. And I'm going to add 1012.5 to this side to balance the equation. Now I've got a balanced equation, and I'm going to write it in its completed square form. So I get x minus 22.5 squared plus 1012.50. And this means that at x equals 22.5, I'm going to have my vertex, the max point, and the max point is going to be 1012.5, and this will give me the maximum area of that rectangular space. That's going to be the area here, 1012.5, and the side length x is going to be 22.5. And we can graph this to find the max. We've in this case did completion of squares. And this will give us the maximum possible area of that space given the constraints. So if I were to kind of draw it a little bit more accurately, I'm going to end up with 22.5. So I'm just going to erase this here. It's going to be 22.5 along the one side. It's going to be 45 along that side, and that area is going to give us the maximum possible space in here, and that works out to be 1012.50 meters squared. The last part says identify any assumptions you made using this model function that you wrote. Well, one assumption I made is that the building was long enough to cover one side. It is possible that we have enough fencing that it's going to make the rectangle here, but then it's going to go past the edge here and then wrap around, and then that would give us a different rectangle to work with, a different area. So I draw it a little bit better here. It's going to look like this, and then I can have this little bit here as an extension. That means that part of that 90 meters could be going towards there. So that's an assumption I've made, is that that wasn't the case. If this was a short building, okay, we may be able to wrap around like this. So the reason why this problem says we have a long building is so that we make this assumption that one side, entire side, can be made up of the building.